starting almost 1 hour late, right? So I don't want to hold the audience too late. So maybe a few places I'll skip some slides, so bear with me, okay? Because I didn't change the talk in the meantime because I wasn't too sure when we'll
But
read.
but sir, it's okay. Like all are our own students and faculty members, so we would still like to hear you, but as per your convenience. I'm
Okay,
sure
fine.
that.
So
Yes,
I'll
yes,
try to then finish off well
yes,
before 1:30, let us say. So
yes, yes.
wonderful. So I was telling you about the various agencies which have supported our work, which I'll be talking about in a later part of my talk. And ACIB, nanomission, though not mentioned here, is also a part of Department of Science and Technology. Then there was a private Jamshedji Tata Trust, and it was mentioned as the Jane Tata Chair Professor. We had access to that funding, and that was very generous. And more recently, extremely generous support in the form of CSIR Bhatnagar Fellowship that I'm very happy to acknowledge. So what this wonder material that I'll be talking about at a later stage and I'll introduce to you is really a new generation of almost miraculous photovoltaic material. And I'll try to show you why we consider it to be miraculous and why everybody is very, very excited about it. And that particular class of material will be this organic, inorganic, and that's why you call it the hybrid perovskite structure. But that will come to later. Let's start with the idea that I'll tell you what the plan of the talk is, which is first I'll talk about energy, basically its various usage and components. And then I'll try to define the problem because when I was young, we were afraid that actually petrol or petroleum products will run out very, very soon. It hasn't happened. I mean, we have lived our life and it's been many, many decades. It may not be running out. It will run out eventually, but not yet, not immediately. But there are other concerns, other aspects that I'll try to point out. And so the problem will shift from not just because it will eventually run out, and that problem can come at a later stage. Right now, we are facing other problems, and that I'll try to define for you. And then how is humanity as a species is trying to rise up to meet this challenge is what I'll try to explain to you. And then I'll talk about some success stories, how when you all work together, the kind of differences that we can make. And then that will take me on to discussing the role of photovoltaics in contributing to the solution to this problem. And then I'll introduce this new material. And then I'll talk about some of the results, not all of it, very, very specific. So basically, the idea is that I'll start with a very broad idea, defining energy, then slowly narrow it down through problem, the challenges, how we meet the challenges, and slowly focus down and finally talk about a particular material that is relevant to this big picture of the energy crisis. And that's why I've arranged it in that particular fashion. In preparing this talk, I've been helped by three people, an ex-group member, Dr. Sharda Govinda, who helped me in preparing several of the slides. And also a few of the slides I borrowed from my colleagues, Wolfgang Eberhardt and Prashant Kamat, and I would like to acknowledge their contributions. Wherever I have used their slide, you'll find at the bottom, there's a footnote saying that the slide taken from slides. And I also apologize, some of the slides are a little old. I had prepared this talk a couple of years ago. So, but the general trend that I'll be talking about remains the same. So the concerns that I'll be expressing are still relevant today. So let's get started. I talk about energy and I'll try to define energy in terms of its usage and component because energy is a very vast thing. We need to define it and I'll, in a moment, define. But before I tell you that, one thing that we need to understand that energy is absolutely central and in fact, completely dictates the living standard of human beings. In fact, there's this famous plot. If you plot for every country in the y-axis, the GDP, per capita GDP of the country, and on the y-axis, if you plot the energy consumed by per person in that country, then you find in terms of kilowatt hour per person, And there's the GDP per person of the country. And the each dot is a country. The dot size is approximately its population. And that's why China is big, India is big. And also this rectangle that I've drawn covers these countries, which if you add up, which if you add up the population of, will represent half of the global population. Immediately, you can see half of the global population is actually using a very small amount of energy per person. And most of the energy is being used by the remaining population. And this particular population is almost devoid of ready access to energy. And I'll come back to this because this is very important to realize this, that energy is central to improving what we perceive to be the standard of living. Where does this energy come from? All this energy that you are spending in quadrillion British thermal units? Well, the basic energy is supplied by oil, natural gas, and coal. Then there's biomass, nuclear energy. Then there's standard renewables that we talk about today, wind, solar, biofuels. And then there is hydro and geothermal. Out of which, the first three are the conventional or the non-renewable source. They will run out eventually. And this is the category which we call renewable, or their lifetime is so long, even if they're not renewable like nuclear, that we don't have to worry about their running out eventually. And you can clearly see that our reliance, because what we are showing in the y-axis is the amount of energy being extracted from that particular source, oil. And that tells you that these three together, which is the non-renewable and conventional source, dominate the energy spectrum. So most of our energy requirement come from the non-renewable oil, natural gas, and coal. And much smaller amount comes from this non-conventional and renewable sources or sustainable sources, so to speak. Where does all this energy go into? I showed you where the energy comes from. How do we use the energy? We use energy in many different ways. In transportation, if I broadly classify, in transportation, in residential or commercial, industrial use of energy is required, and electricity generation. And the color coding for each, in fact, the first bar is the actual data of 2016. The other two is 2025 and 2040, and these represent the expected trend. And color coding in any case is actually telling you where the energy is coming from. So for transportation, green corresponds to oil. So almost all the energy comes from oil because, petrol, diesel, etc. These little ones on the top blue is the electric vehicle and other sources that one can be thinking of. Residential, there's a lot of still oil is required, natural gas is required, coal is required, and some biomass is required. Similarly, industry and electricity generation. So in order to address the energy problem, it depends on which sector or which particular source of energy I want to tackle. For example, if I perceive oil as a problem, for whatever reason, then you can see that oil mainly is used for transportation sector. So then the transportation sector should be my focus. We should be looking at transportation, how to make it efficient, either more oil efficient so that oil use comes down, or some other technology which will replace oil altogether. And that's why there's so much of discussion today of electric vehicle all over the world. If we think no, coal is a problem because coal is extremely polluting, then immediately you can see that it's the electricity generation that I should be paying attention to, because main consumption of coal is in the electricity generation and some amount in industries. So in order to address the coal consumption, I must have alternative technology coming in for electricity generation. And that's where photovoltaic will become important when I come to talk about that. And in some sense, it's important to focus on the electricity generation itself, because as you can see in these four groups, it is the electricity generation that takes the cake. That is going to use maximum amount of the energy. So in order to address the energy problem, we cannot afford to forget about electricity generation. And that's why eventually I'll focus on through photovoltaic, which is electricity generation, and into the particular wonder material that I'm talking about. So that's the energy. I've given you an idea of where the energy comes from, how we use it, and how energy supports the standard of living. Now, let me try to define you the problem, because I've not said anything about the problem so far. Now, this is the picture that I have already shown you, that living standard is being supported. And you can see that if I want to improve my living standard, which is measured as GDP per capita GDP, then I need to also simultaneously increase the energy consumption per person. And you cannot deny the legitimate aspiration of every country to improve its situation, which means every country is struggling to move up in this direction, but they cannot do this moving up unless they move up in that direction also. So every country, as it wants to become more advanced, wants to improve its GDP per capita, will end up also using more and more energy. What is the consequence of that? The consequence of that, this was in 2016, and if you see, look at India itself. Every year between 2013 and 17, and in subsequently, the energy consumption per person per year has steadily increased by 5%. Remember, it's not because of population increase, because it is normalized by the population. That means on an average, each person is consuming more amount of energy because our GDP is growing. Of course, our population is growing. That means there's a compounded factor and we're using more and more energy much more rapidly. So if I want to look at that, and here is the total amount of energy being used, not per person, in different countries. In 2016, and you can see United States, this one, all of Europe together here, China alone here, India here, all other Asia Pacific countries put together here, Middle East, Africa, and rest of the world. And now let me put also the sum of the populations in billions. The population in billions, China is close to 1.4, we are close above 1.3, USA is around 0.33. See that they have a population which is 1/4 of Indian population, and they use 4 times more the energy, which means per person, there's a factor of 16 difference in energy consumption. And you cannot tell an Indian or a Chinese or an African that don't use energy. All of us have the aspiration of having more energy. And if India or China today would begin to use energy at the same rate as the average American, then it will go out of scale here, because that use will become 16 times more, and that goes out of the scale. So will China go completely out of scale if I have to use energy at the rate that USA does or Europe does. And this tells you that energy requirement would become so large if everybody aspires to have the same kind of affluence today. And that is why, and in fact, you can see that it is happening. China's year on year, it is expected to increase. This is 2016, 2025, 2040. The expectation is steeply increasing energy consumption, also with India. In fact, these two are increasing much faster than Europe or USA would be increasing, simply because our aspiration and our growth possibilities are much larger. And if that were to happen, and this is where Gandhiji long time back had raised this question, saying that it took Britain half the resources of the planet to achieve its prosperity. And if everybody wants to achieve that prosperity today, then how many planets will India alone require for its development? We cannot sustain that on this planet. We do not have the resources. So we have to have a different model of development and different model of energy consumption, utilization, and generation. And there are serious other consequences. It's not just natural resource issue. It's not a resource issue alone. And in order to convince you of that, what I'm showing over here is all these dangerous gases that are being emitted because we are consuming energy by burning fuels of different kind. Starting from, let's say, beginning of the Western calendar, 0, if we follow how carbon dioxide, methane, and nitrous oxide has been produced, you can see that was pretty much flat in this scale till something happened here. And it suddenly started increasing and increasing completely out of scale. What are these years? These years, if I mark for you, that these 2 years I've marked 1760 to 1840. Now, what happened between 1760 and 1840? If you read Toynbee's history book, you'll see that the traditional definition, starting from Toynbee subsequently, are the years that are seen as the Industrial Revolution. Mechanization of production. The means of production became mechanized. And that mechanization required energy. Energy requirements steeply went up in order to get the advantage over other countries by having production much faster, so that the scale, economics of scale came in to reduce the price so that the product can reach more number of people who can capture more markets and be more affluent. And after that, there was no stopping. It steeply increased. Now, what looks to be steeply increasing, if I plot for you what happened after 1900, there's a lot of lesson to be had from history. So what I'm going to now plot for you is this little part beyond 1900, what has been happening, only that part. And you'll find that it's not been uniform. In fact, in the beginning, even though it was steeply increasing with respect to the scale from the beginning of the calendar, Western calendar, to 1900, but that with respect to the later rise of consumption of metric tons of carbon emission was actually slow. What happened here? This is the year, as you can see, is between 1940 and 50. This is the end of the war, the Second World War. After the Second World War, there was a very steep rise in industrialization and energy consumption. And you can see that energy consumption directly relates to the amount of carbon emission. And it was sort of stabilizing here and then started increasing again. And one would like to ask the question that this is the post-war activity. Then it was flattening. What led to this increase again? And while searching for an answer to this, I found that another plot, completely unconnected, so it would seem, if I plot it over here for you, which is Chinese control of the world economy, and that is what is plotted over here, this red curve, in function of year 1980 onwards, matching with the scale here. And this is the China's control share of the world economy. You can see it was flat and then started increasing very steeply. And China started using energy very enormously, as you've seen. Now China uses maximum energy as a country all over the world. And that has pushed up once again the carbon emission. And now if India wants to get there, then it will push it up even more. So that's why, and this carbon emission has drastic consequences. Look at the image, photograph of the same place, same time, separated by 80 years or so. 1921, glaciers were there extending all the way up. All the glaciers have vanished by 2009. And these are direct evidence of the global warming. Here again, 1900, the glacier was extending. 100 years later, the glaciers are all gone. In fact, from these kind of images, one knows that 50% of the world's glaciers have vanished from the face of the earth because of the global warming. And that is a direct consequence of this tremendous increase. And the consequences of this, if we don't reverse this process, is really enormous. Our ecology will ecological changes will be so much that it might become completely disastrous and we can have a complete collapse. In fact, people are talking about the extinction of species, that the dinosaurs vanished. In fact, scientists have figured out there have been many such phases of extinctions, and they suspect that the one more great extinction has just begun. It may take many thousand years for it to be true, but the survival of the human as a species is in question if indeed we are going to face another mass extinction. And that mass extinction might get triggered by these environmental changes that we are bringing about. And we just cannot afford to do this. But it is not only that thousands of years. You may say, okay, how the hell do I care? Another 1,000 years later, it's not me, not my children, not my grandchildren, not even grandchildren's grandchildren. It would need so many generations. I don't want to care about it. And something will happen magically, even if we don't worry about it. First of all, Catastrophic changes take place, and they don't take place slowly and continuously. The environmental change will take place and will trigger a catastrophic change at a time that you cannot anticipate. That is the nature of catastrophes. And that sudden change can bring about a very rapid mass extinction process. But even if that doesn't happen, let me argue that actually an extinction process has started because of the pollution. What I'm showing you is the map of India, and it's color-coded in terms of the most pollutant that affects the health. This is the particulate matter, which are of 2.5 micron size, and how many micrograms per cubic meter is there in the atmosphere. And you can see that these are all red belt. This is where you know the smog covers, and Rajasthan also. And you'd find that a large part has yellow-red, and you'd think these are blue, so this is good. Let me point out this blue, the best one in Kerala, less than 20, is still sitting above the WHO recommendation. WHO recommendation in the world, no state in India has the particulate matter level lower than what is the WHO standard, which is 10 microgram per cubic meter. Kerala is below 20, so close to that, but not within the limit that it should be. India itself has its own standard. You may say, I don't care about WHO standard, but it's 40 microgram per cubic meter is India's standard, and 77% of India's population is exposed to a higher level than that. And that tells you how bad our air condition is from this particulate matter. And this particulate matter is a direct consequence of our energy usage, the way we generate energy at various stages of our lives and society. In fact, it is known, and this was a very famous paper that was published in Lancet, Planet Health some days back, which pointed out that the total disease burden in India, 8% of that can be related back to pollution. And 11% of the premature death in India. Today, you, I, our children, our grandchildren are dying. 11% of the premature death. People didn't have to die, but they're dying because of this pollution. So we cannot delay the discussion on the energy crisis. So it is not a question whether the conventional sources will run out. Of course, they'll run out. That is the nature of non-renewable sources. And the debate can be how long it takes, etc., etc., etc. But that's not the issue that is facing us right now. It really is the cost that you have to pay, not the price. Cost in terms of our health. Cost in terms of the very notion of survivability of the species. And is this a sustainable model of the energy generation, energy consumption? And also remember, these natural resources are very precious in the sense that we do not know how to replace them in many, many applications. In metallurgy, where you need coal, you need coal. There's nothing else that we know of as of now that can replace that. Air traffic, as of now, we do not know a viable alternative to the aviation fuel because we need that kind of energy density. There are many petrochemicals that pervade our existence, the modern existence, and we do not know how to replace them. So you need to preserve your natural resources for things where we don't have any option as of now, and you want to extend their lives as much as possible. So that really the question is between non-renewable and renewable, between polluting and non-polluting, between destructive and sustainable, between invasive and non-invasive. For me, the choice is very clear. So having defined the problem for you, let me point out how humanity, on one hand, creating this destruction, but on the other hand, also is meeting up to face this challenge and found solutions to this challenge. What is the challenge? What I've given you is, as a percentage, the source of energy, starting from 1970 to about 2010, 2012, 2015. And you can see more or less it's been steady over the last 30, 40 years. Coal, gas has increased a little, which has helped us to reduce the oil or dependency on oil. Nuclear rapidly increased, but then there's been a lot of political pressure and social pressure, because of which nuclear, the percentage contribution is decreasing. And this is the hydrothermal, which has remained more or less steady. So this is called the power generation mix in terms of percentage. Total energy consumption has gone up a lot, but as a percentage of that, where the source, the percentage contribution hasn't changed. And remember, this is the non-renewable. So non-renewable part, we started at about 70% in 1970. Over 35 years of effort, we have brought it down to 60%, only a 10% decrease. The challenge really is to bring it down to about 30% by 2050, where our dependence on the oil will become almost zero, gas will remain, coal has to come down drastically, it's very polluting. Hydro will not be able to increase too much, and you can see what is going to increase is this thin part here, which we are just in the process of expanding. They must expand very large. Wind and solar must come in big way, and 48% of our power generation has to be from solar and wind, and 64% will have to be from renewables. This is the challenge. And how are you meeting that challenge? So basically, if you look at the world today, the dependency on coal, gas, and oil is here. There's a lot of dependence on nuclear as well as hydro. These two will not increase very much. So these small ones, this wind here, solar thermal, and maybe solar photovoltaic, these have to increase very drastically. In fact, India is in a very bad situation because its dependency on coal is huge. And that's the reason it's very, as I was pointing out, it's very polluting. How are you rising up to the challenge? Here is a curve that tells you this is the hydropower starting from 2007 to 2017. How we are increasing the hydropower. It's increasing, but not very much. It has increased 37%. But then look at this wind power. This blue has increased by 443%. The solar was so small that I didn't even bother to put it into percentage because it would go into more than 1,000% increase. It's the solar power. So we are shifting very rapidly the component of power to be generated from the solar, wind, and hydropower. Now, let me point out some of the success stories, not just India specific, but the world. The success stories are really mind-boggling if you think about it. Because we human beings have a tendency of getting used to any change that comes, any technological change that comes. I mean, if I look back at my childhood, which didn't have TV, didn't have telephone in most of the household. In fact, I remember when I came back from Germany and I wanted to have a telephone, I had to pay a whopping amount of money and then wait for 3 years before I could get a telephone line. And there was a wait for 3 years under a very special category that accelerated one's getting telephone. But now every child has a telephone connection, is able to talk, not only audio, but video. And we have taken it in our stride. Even the grandparents know how to use it. Great-grandparents know how to use it. You get used to it. You get used to it so much that we don't look back and see how well we have been improving our lifestyle. So I want you to realize some of the success stories about this. Energy, we need to break it up. I've been talking about power, but I've talked about generation, but we need to talk about transmission and utilization. There are 3 ends of energy. Where you generate it, how you transfer the energy generated at one place to the place of its utilization, and then you have to ask how it is utilized. In terms of electricity, the one that I talked about as a main chunk of usage of energy, let us look at the entire chain as it was when I was a child. Energy, most of them in India even today are coal-based, thermal power stations. If the energy content of the coal is 100 units, I directly lose about 62 units of it as heat. So there's a 62% wastage of the energy. Only 38% of that energy is pumped into the transmission lines. The transmission lines are not bad. They lose only about 2% of that energy. I get 36 units into the house. And then we had these incandescent lamps, which would take these 36 units and give me out 2 units of energy in terms of light, and 34 units of heat would be going on. So in terms of heat, 62 units plus 34 units, which is 96 units, would be lost. I would use only 2 units, another 2 units of transmission loss. So you can see how lossy the entire mechanism was. And so we need to look at how to improve upon this utilization, generation here, and utilization here. The transmission seems to be reasonable for the time being. And that's where one talks about solar photovoltaic. Because photovoltaic is not in terms of generating coal, which is a non-renewable and therefore is undesirable and polluting. Solar energy is coming to the sun, whether you use it or not. If this energy can be used, I don't care about the loss, because it would have been 100% loss. Anything that you use is usage. One problem of it is that it is intermittent. If there's cloudy sky or in the night, there's no generation of electricity. But my generation of electricity must remain constant, and on order, I must get electricity. And this intermittency is a problem, and that has to be addressed. And that's when we need to store energy. That means generate the energy when it is available, generate more than what you need, and store the excess energy. And that excess energy can be pumped back into the transmission line whenever somebody needs, even if I'm not being able to generate. So then with photovoltaic, I must have storage of some kind. The particular kind of storage that I'm going to talk about is going to be batteries. And then at this end, incandescent lights have been replaced by LED. Another spectacular success story that I would like to talk about. So I'm going to talk about photovoltaic technology, battery technology, and LED technology, and how it has transformed our life without even our knowing about it. That is, we have realized a dream, and we have not even realized it, that there's a quiet revolution that has taken place. This shows you the price, module price, the dollar price of per watt of energy, that power that I'm generating. How it is dropping from 1976 to 2018. And you can see that it has dropped very drastically over this, from $70 per watt at 1976 to about 2018, it's come down to $0.25 per watt. What is plotted in the x-axis is not the time, but the number of modules that are being produced, or the total capacity of power that is being produced. You can see that the capacity, as it increased, brought down the price. And one can also say, because the price was coming down, the capacity could be increased because the scale could be increased. So they go hand in hand. It took us 42 years to bring down the price by a factor of 280, a factor of 300 drop in the price. Despite inflation of all other material, all other things in our lives, actually over these 42 years, the price has dropped by a factor of 300. And that tells you what a spectacular development technology has given us to give rise to this decrease in price, whereas everything else, the price increases. And that has made the possibility of this fantastic increase in the utilization of solar photovoltaic today. The batteries I was talking about, batteries are seeing year to year a 20% drop in price for every kilowatt hour of energy that it stores. And that's a spectacular, in terms of dollars, again, $1,000 to $273 for 1 kilowatt hour of storage, just in 6 years. And if I again plot the similar way, you can see that from $1,000 per kilowatt hour, I've come down to only this much, slightly above $200 per kilowatt hour, is a factor of 4 reduction in just 7 years. There's again a spectacular reduction of price when everything else price goes up. And that has made possible electric vehicle, all appliances all over the place, and battery has pervaded everything. And we expect it to further energy density as well as power density, and the price to go down and the energy and power density to go up. So it's seen a reduction rate of about $105 per kilowatt hour per year so far. And the most spectacular of all is the LED that we don't even realize. LEDs, when they started, this is a plot of lumens per unit of LED that I had. It started with very low value, very faint sources, and how it has increased by more than 1 million times for 1 unit of LED. That's why they're so bright today. You have LED TVs, LED searchlights, LED flash lamps, LED everything. And that's possible because of this tremendous increase in luminosity. And that luminosity increase per package has also brought down the cost per lumen very, very drastically, just over these 40 years. And in these 40 years, per unit of lumen, the cost has gone from $50 to $0.004 US dollars, 0.4 cents, which is to say that in 37 years, we have had a cost reduction of 12,500 times. There are no parallel of this in any other technological development that has given rise to this kind of price decrease. And in fact, because of that, the adoption of LED into technological adoption of LED into human existence is possibly one of the fastest technology shifts in human history. In fact, if you know here, what I'm showing from 2010 to 2020, let's say, the hybrid electric vehicles in 2010 was about 1%. They've come up to about 7%. Solar PV wind occupied about 12%. Now it is about 30%. LED starting from 1% has captured in the meantime 70% of the lighting applications in the world. And in fact, it's supposed to become close to 100% in another few years. So you can see how quickly it has made inroads and taken over our life completely. So that's where the success stories I wanted to tell you. Now let me tell you about the electricity generation and why we should think of photovoltaic as the application. There are many different ways of generating electricity, which are renewable energies: hydropower, tidal power, waves, concentrated solar power, biomass, photovoltaic, geothermal, wind power, many, many. The reason I, as a scientist, am very much interested in photovoltaics and many others is that any technology growth actually has this S-curve. S-curve is this one, which says that in the beginning, there's only basic research. Application or market penetration is very small, and scientists don't care about the market penetration. They're busy with understanding the fundamental aspects. And market penetration is very, very slow, but they're putting in a lot of research effort and understanding rapidly the system. As they begin to understand more and more, the understanding part decreases and the market penetration begins to increase and becomes very steep, and then again begins to saturate. A mature technology begins to saturate and the market penetration comes to a constant part. You can put in more research effort, but you're not going to increase either the understanding or the market penetration. And different renewable energy technology have marked where they exist today. And it turns out that the photovoltaic is at the most exciting cusp where both knowledge generation and market penetration are going hand in hand very, very rapidly. So it's a very, very exciting area. And of course, photovoltaic is going to be there because solar power is constantly coming and will come for millions and millions of years, and they will come whether you want it or not. So converting that is the most sensible thing to do. This has been a success story in India itself. We have one of the most ambitious plans of renewable based on the solar photovoltaic. 170 gigawatts by 2022. That was the projection in 2018. There's some slightly different projections now available. Solar capacity increased by 370% in last 3 years between 2015 and 2018. And the power generated actually reached a price that became competitive or lower than the conventional form of energy. Because unless it becomes feasible, economically feasible, it's not going to have penetration into the market. And that became possible. Now I come to the question of this photovoltaic and the excitement of the new material class. Now that I've told you why photovoltaic is interesting to us. And I'll quickly go through some aspect of this organic, inorganic hybrid perovskite. Hybrid refers to the fact that it's not purely inorganic and not purely organic. It has a mixture of both organic and inorganic, and it's a perovskite structure. The perovskite structure is a very simple structure. You think of a cube, and that cube, typically a perovskite has a chemical formula AbX3. A and B are typically some metal ions, and X is some anion, most often oxide ion, doubly charged, negatively charged. But the interseries that I'm going to talk about will have halide here, chlorine, bromine, and iodine. That's a very often they are also distinguished from the conventional perovskites, oxide perovskites, by calling them the halide perovskites. And the structure is, think of a cube. In the cube, at the cube corner, you put this B metal ion. At the body center position, you put the A metal ion. And edge, this cube edge, at the center of that, you put the X ion, which normally, as I told you, oxygen 2- ion, but in our case, it will be chlorine, bromine, or iodine at this position. So there's an octahedral unit around the B of this anion, and those are shared in three-dimensionally to make a three-dimensional structure, which is called the perovskite structure. And they're very, very versatile structure. They give rise to many, the perovskites and their derivatives give rise to many properties: multiferroics, charge transfer insulator, metal insulator transition, colossal magnetoresistance, high temperature superconductor is a variation of the perovskite structure, etc. But then organic and inorganic parts are there. So what it says is that instead of at this A side putting a metal ion, I'm going to put an organic ion. Here I've put a methyl ammonium ion here. I can also put a form of medinium ion there to stabilize the structure. That's why I call it the hybrid structure. And it turns out to be very efficient photovoltaic material, and it's extremely easy to make a solution based. So basically, today we're completely dominated by the silicon photovoltaic, and I'll show you the results of that in a moment. But that needs tremendous amount of energy to make. In fact, sometimes one asks the question, does a silicon module generate enough energy in its entire lifespan that it is required to make that module? Because you have to melt the silicon. It's a very high temperature process and very energy intensive. But these materials that I'm going to talk about can be made at 100 degree, 200 degrees centigrade in a solvent, solution based. So making thin film is very easy. So they have many attractive aspects. What I'm showing you here is a very busy curve. Don't get worried. There are different colors and different symbols. Every color represents a particular kind of technology. And what this plot is following as time goes by, so this is years from 1975 to up to 2022 here, 2021 here, how different photovoltaic cell efficiency went up. Since different technologies cannot be compared with each other, each technology is connected by a line with different color and symbol, and you can see how the efficiency of that technology went up as time went past. We are talking about silicon technology. That's the one that we're using. And let me trace it for you. This is the silicon technology that you use, multicrystalline silicon technology. And you can see that starting from somewhere here in 1980s, early 1980s, it had something close to 15% efficiency. It has come to something like 24-25% efficiency today. Over this many years, nearly 40 years. This is the single crystal silicon technology. I can trace that for you. And that also has, starting from somewhere 13% from late 70s, has come to about 26-27%. How long did it take us? It has taken us 43 years of improvement and billions dollars of investment to improve the efficiency from about 13% to 27% here, 14% to 26% here. Billions of dollars, 43 years. The technology I'm going to talk about based on this hybrid material that I talked to you is actually plotted here. It started seriously somewhere near 2012. And in the past 7 years, and I'm tracing it for you, it has become as efficient or even more than the multi-crystalline silicon technology, just in 7 years' time. And investment has been minuscule in terms of time and effort. So everybody is excited that such a steep increase in efficiency. Not only the efficiency, it turns out that this material is fantastic absorber of light, because you need, for example, silicon is a very poor absorber of light. You need to make it quite thick, and making it thick makes it more expensive, heavy, more breakable, and all kind of problems. So people are looking at how to make it thin. One of the technology that was proposed is the dye-sensitized solar cell, and it was shown that you can make it as thin as 10 micron, then device. Then came solid-state dye-sensitized solar cell, and one could bring down the thickness to about 2 micron. Then that same technology evolved into extremely thin solar cells, which became about a micron thick. And the technology based on this material can be as thin as half a micron thick. So you can see that it is a fantastic absorber, so you can make extremely thin solar cell and have still very good efficiency. This actually started, just to give you a sense of the history very quickly, started around 2006, 2008. This gentleman, Professor Miyasaka in Japan, was working with these materials. These are the materials that I'm going to talk about. And he could find very low efficiency, 0.3 to 0.2% or so. And then it also had very low stability, only several minutes. Till Namgui Park's results showed a 6.5% efficiency. It still didn't catch on the attention of the entire world till Namgui Park and Henry Snaith at about the same time showed that these materials can give 10% efficiency. When people saw that, and that's the 2012 papers that I'm talking about, once people saw that it can have 10% or more than 10% efficiency, everybody jumped into it. And then within this short time of less than 10 years, we have gone from 10% efficiency to about more than 25% efficiency, close to 26% efficiency, which is spectacular increase. Why is this material so good? Now, let me tell you what is a photovoltaic cell. A photovoltaic cell, like a silicon, for example, has a PN junction. By doing some doping, you make a PN junction so that there's an electric field inside, such that now if light comes, light will generate an electron and hole. The electron will go towards the positive end and hole will go towards the negative end. So electron and hole will get separated. Once they get separated, you can collect them outside and you can drive an electric current outside and make use of that energy. For example, an electric bulb here, or run a motor or whatever you want to do. So you want to absorb. So the properties that we need for a good photovoltaic material, it should be a good absorber of light. It should allow a very effective separation of the charge carriers. And since I'm interested in the energy or the power generation, the power is not just this one electron and hole, I get 1 unit of current. But remember, power is current multiplied by voltage. So the total energy generated is current multiplied by voltage, multiplied by time. So the current, while maximizes current, you also want to maximize the voltage difference across it. And so you want a high open circuit voltage. It turns out this particular material that I talked about is a fantastic absorber of light. For a single component, we know that the band gap should be about 1.4 electron volt to maximize the power output. It has a very close to that band gap. Silicon has an indirect band gap, which is very poor absorber of light. It is a fantastic absorption coefficient. That's why you can make it so thin. It has very long carrier diffusion length, and it can give you open circuit voltage up to 1.1 volts, which is very large. So everything looks to be good. Is that all? It turns out that it is not all, and there are many scientific open questions, and I'll address a few of them in the next 10 minutes before I close. Can I take 10 minutes? Otherwise, I can close here because I've given you a feel.
Sure, sir. Of course, you can take.
Okay, fine.
We all are here. Thank you.
Thank you very much.
No problem, sir. Thank you, sir.
Thanks, sir. So I'll just tell you a few questions that we have asked and how we try to answer them and understand them. And so this is for my young student friends to how to ask the question, what kind of question we ask, and how we try to go about giving answers to them. So now we are coming to the question of what we understand and what we don't understand. And a very large number of people have contributed to this. I'm not going to read out all their names. These are from ISCR group, and these are from my colleague, Professor Anshu Pandey, Professor Gurrao, and his group their group members who have contributed. I've extensively collaborated with my colleagues, Professor Sundareshan, Professor Narayan, for the results I'm going to show now of JNCSR. I also collaborated extensively with the theory group in Vienna as well as in L'Aquila, and I'll not be talking about all the details of that. In the early days, these are the papers long time back that Sharda Farad thesis, Sharda and Bhushan, who was a postdoc, published on this particular subject in the early days. And Menno was the main driver of the theory part of the research, and these are the papers that were published at that time. More recently, Ashutosh Mohanty, who has again since then finished his PhD, Sharda finished a PhD long time back. Ashutosh started working on it. More recent time, he published this paper. And there's another collaboration with the Beers scientists, which we've published 2-3 papers, not all listed here, and some unpublished results. I may not go to the unpublished results. I'll talk about some of these results just to give you a feel for the kind of questions that were asked. This is the perovskite structure I already told you about. And the first thing you should notice is this methyl ammonium, which we believe we put in there to stabilize the structure. And I'll be referring that as methyl ammonium as Ma. This Ma unit is a non-centrosymmetric. That means it has a dipole moment because it's an asymmetric moment. And it turns out that it has a large dipole moment. Now, then the question is, in the solid, all these dipole moments, if they're pointing at the same direction, then it can be a ferroelectric, if I can even switch their moment. Now, if it would be ferroelectric, that would be fantastic for photovoltaic application. In fact, there's an entire subfield where people are searching for ferroelectric materials, which can be used as photovoltaic, and I'll tell you in a moment why. But most of the ferroelectrics are very poor photovoltaic material because they have very large band gap. So they don't absorb the solar spectrum. But we know this one absorbs solar spectrum very well. It has a very good band gap. So the question to ask, and this is the question that Sharda asked, this is the title of her paper, is a more generalized than ferroelectric because every ferroelectric material must have a polar structure. That means a non-centrosymmetric structure. And why is ferroelectricity interesting? It is interesting because, again, I told you, normal silicon, for example, has a PN junction. And so the electric field is very close to this junction. So if you create an electron hole close to the junction, the hole will go that way, electron will come this way. But imagine that if you create the electron hole far away from there, this electron and hole don't feel that potential gradient very strongly. They can recombine, and so the efficiency will go down. But if you have a ferroelectric material has a polarization throughout the material. So quickly, as soon as it is generated, it doesn't matter where the electron and hole is generated, locally, it will go to the positive end, all the electrons will go to the positive end of the ferroelectric domain, and the hole will go to the negative end. So they get separated. Once they get separated, they cannot recombine. And in fact, then they travel through the this ferroelectric photovoltaic material, avoiding each other all through, because they have their minimum of energy at different places, at the two ends of the dipole. And so they move, avoiding each other so they don't recombine, so you get higher efficiency. And that's why one is excited about ferroelectric. So the questions that we asked, what makes it so good? Can ferroelectricity be one issue? That means a more generalized question, what are the dipoles doing? The dipoles that are there daily. Are these dipoles ordered? If they are ordered, are they ferroelectrically ordered or anti-ferroelectrically ordered? Because if they would be anti-ferroelectrically ordered, then this separation will not take place because the dipoles cancel each other. And if they're disordered, are they disordered statically, like a glass frozen in different direction, or they're dynamic, rotating somehow? So this is a question. And then the other question, that once I create this electron and hole, they attract each other with a potential that we call the excitonic binding energy, that energy of binding of the electron and hole. I must overcome that to separate them. And I would like it to be small, this binding energy, so that I can easily separate them. But if it is large, I won't be able to separate them. And so we wanted to know what the excitonic binding energy is. It turns out that in the literature, the energy estimate was from 2 to 100 milli-electron volt, a very widespread, which means that there was no agreement on that, though it's so important a question. So there's no consensus when we went into this and we started asking these questions. So let me ask the question of the ordering of the dipole in the ground state as well as excited state, and I'll explain that in a moment. I may not come to excited state like this. So how can I measure if something is ferroelectric or not? I look at the PE loop measurement. It's just like in a magnetization MH loop measurement. You apply an electric field and you measure the polarization. So we apply the electric field in this direction, positive end, negative end, and we see the polarization, and like MH loop, you have a PE loop in a ferroelectric state. You can see at zero polarization, a zero applied electric field, it has a finite polarization. That's the one that separates the electron and hole. There's another, this is our own work. We had shown a special, very, very special, it was published here, a ferroelectric material with a very low band gap, so that it can be applied to photovoltaic applications. But I'll not talk about that. Oops, something happened.
Any problem, sir?
My screen has gone blank. Just give me half.
Okay, it's okay, sir.
There's a lot of noise and I'm back. Is it okay to see now?
Yes, sir. We can see the screen.
I'm extremely sorry. It's something I did with the mouse that suddenly.
No problem.
So basically, so the loop measurement we did, and we found that there is no, at low temperature, I know this material to be antiferroelectrically aligned. So I don't expect the loop, and I see the polarization. It looks like this. And at room temperature also, it looks essentially like that, telling me that the dipoles are not ferroelectrically aligned. We'll look at it also in terms of second harmonic generation. Let me skip that part. Essentially, there's no second harmonic generation that says that the structure is not non-centrosymmetric. It's a centrosymmetric structure which cannot be ferroelectric. Then the question comes, then what are the dipoles doing? Because dipoles are there. Now the dipoles, in order to understand their properties, we look at the dielectric property. And what I've plotted here is the dielectric constant of this material, MAPBBr3. It's a complicated curve. In order to make you understand this one, I will walk you through. First, I'll take a different material, cesium. Cesium has no dipole. So I'll look at the cesium lead bromide and ask what is its dielectric constant like. Its dielectric constant is actually plotted over here. It's almost temperature independent, frequency independent, different colors of frequency dependence right here. So if dipoles don't contribute to the dielectric constant, I expect this behavior. Then I go and look at my compound, MAPBBr3, where Ma has a large dipole. I look at the low temperature where I know that they're antiferroelectrically ordered, which means the dipoles will not contribute to the dielectric constant. And I find it looks like the cesium analog. But then at this temperature, I find a huge dependency, 1/T dependency of the dielectric constant that tells me that the dipoles are rotating freely. This is like a paraelectric state where dipoles can rotate and respond freely. And in fact, our theoretical simulation tells us the rotational time scale of about 5 to 10 picosecond. So they're rotating very, very fast. There are many consequences of that I'll not go into that today. We also looked at the excited state because there's this interesting story that you create an electron and hole. The dipoles are rotating, but now you've created an electron and hole. The electron gets attracted to the positive end. The hole gets attracted to the negative end of the dipole. So the dipole now has electron and hole attached to it. So it might find more sluggish to rotate. And if it freezes, then by dipolar interaction, it can freeze other dipoles. So it's not just the ground state. In the excited state, you may have a polar state. And we also address this fine question of after the photoexcitation, what happens? The way we did, these are the dipoles that are supposed to be rotating. I come in with a photon, which is high energy, which creates an electron and hole.
Hello.
And then I give it a slight time. And at the end of that time, a time delay, I now measure the second harmonic generation and see if the rotation has stopped and I get a polar signal. I'll just tell you the story, end of the result that we did this delay experiment, and then found that there was no second harmonic generated. And so even in the excited state, there is no polarization that develops. So that was settled. I'll just quickly tell you about the excited binding energy. This is the, you can see 6 millivolts to 98 millivolts, all kind of reports. The way we often measure is look at the photoluminescence as a function of temperature. Because the photoluminescence, if the excitonic binding energy is large compared to the temperature, they bind very well and they recombine, giving me photoluminescence. But if the temperature is large, the temperature breaks apart the exciton, and so they cannot recombine, and I don't get photoluminescence energy. So as I lower the temperature, what happens is that slowly, is my video on or that is off, I think, for some reason? Yeah. Okay. So
It's on now, sir.
yeah. So the exciton, if the temperature is large, then the exciton can break apart, and so the photoluminescence intensity goes down. So as I increase temperature, photoluminescence intensity goes down, and it's dictated by this equation, and the excitonic binding energy appears there. And you can see over here, okay, wonderful. Now I'm having trouble. It's not moving. Let me see if it moves now. Yeah. Okay. And now you can see that, let me pick up the laser pointer. Okay. So this is photoluminescence intensity, how it changes with temperature, and I can plot it. But the problem turned out that actually, even if I'm not changing the temperature, but only doing the measurement as a function of time, I find that the intensity is going down very rapidly. The reason it was going down is in order to do this experiment as a function of temperature, you have to put it in a cryostat and you have to evacuate the cryostat. Because if you didn't evacuate, then when you lower the temperature, all moisture, oxygen, nitrogen will condense on top. But as you evacuate, some of the defects get created because you're sucking out something from the sample. And the intensity drops to 1% of its intensity. See, from here all the way down to almost zero intensity. And that had to be avoided. And the way we avoided that is by doing 2-photon experiment, where we go deep down into the sample, which is stable at that, because all this effect happens near the surface. With single photon, since it has a very strong absorption, you get signal only from the surface, and surface gets affected with evacuation. But 2-photon experiment where each photon has energy lower than the band gap, so they don't get easily absorbed. They get absorbed uniformly inside the bulk. And then you can look at the intensity pattern, how it changes. Then you can fit it to the equation and extract what the binding energy is. And the binding energies are estimated here. With that, these are the calculated binding energy, excitonic binding energy you had published long time back. And for many, many compounds. And then compared to that, these are the experimentally obtained values. And that you can see is in good agreement with the theoretical prediction we had made long time back. With that, let me come to the end of my talk by pointing out the outlook. We have to improve the efficiency of energy production. so that it can impact the economics of production, shift the energy landscape completely in order to save humanity, save this planet. The energy auditing of the PV modules are likely to be significantly improved because these are materials which are solution-based. And today, real technological applications are being explored in tandem structures. So with silicon, but on top of silicon, this material is being placed to improve the efficiency much further. And there's great excitement ahead in terms of science and technology. There are problems, the issues that you are addressing. I have not talked about it. These materials are unstable. That's a very serious issue that you have to address. Lead being present certain technological challenges that you have to answer, and defect in these materials have to be controlled. I have not talked about it, but let me end my talk thanking you for your patience. Thank you very much.
Thank you so much, sir. It was such a wonderful talk. We really learned a lot. And thank you, everyone, because of this unfortunate event that happened initially. And I'm really thankful to Professor Sharma, who again gracefully joined this session. So, sir, would you like to take one or two questions?
Sure, absolutely, no problem.
Okay. So first question will be asked by our colleague, Dr. Sharup Kumar Niyogi. Over to you, Sharup. Can you?
Yes. Sir, can you hear me?
Yes, I can.
Okay. Sir, I am also doing some work in the experimental physics. So my question is not a very rigid question, but I am just asking this thing that, sir, there are a lot of research work is also going on in multiferroics. That means ferroelectricity and magnetic ordering, both are there. So if magnetic order is also present, apart from ferroelectricity, then it can hamper the electron hole pair creation, or it can improve the thing. Means I just
okay. So multiferroic, this research in multiferroic is coming from a different technological motivation. The motivation being that if you think about computers have two very important components that are separate today. One is the storage, which is essentially magnetic in nature. And the other one is the processing, which is based on silicon technology, okay, which is electrons charge being used, and the other electron spin being used, magnet and electrical aspect. The multiferroic hopes to combine these two on the same thing, such that you can modify the polarization state by application of a magnetic field, or magnetic state by application of a electric field, and integrate both processing and storage such that the bottleneck of data transfer is minimized. This was the technological motivation, and there are many interesting applications of it too. But with respect to the photovoltaic application, it will be the ferroelectric part that can contribute. Magnetic part is unlikely, at least to the best of my knowledge, is unlikely to contribute, because magnetic field, if present, actually gives a circular motion to the charged particles rather than linear motions, which means that it would deflect the electron and hole. If you have an internal field, magnetic field, deflect the path of the electron as it propagates. That can have, if anything, some adverse effect. I cannot quantify it. I have no idea, but I don't think it would help the photovoltaic aspect.
Okay. Thank you, sir. Yes, I can also understand this thing. Yes.
Thank you so much, sir. And there are 2-3 questions also written in the chat box. So if you're willing to take, we can take 1 or 2 questions, sir.
Sure. Should I pick some of them?
So Dr. Deepto Shikha,
yes,
if you please
so I'm
ask
going
this
to the
question.
next question. Yeah. So next question from Neil: what is biopower?
Biopower, there are many biological systems. First of all, I should give a disclaimer that in many of these issues, I am as much of a novice as you are, whoever is asking the question, because I have not studied them. I can only make a guess, right? So biopower is, there are many organisms that have power generation, electricity or photon generation possible. And that is one aspect. Another aspect is that whether biological mass can be used for power generation. And this is also being explored. These are very preliminary, laboratory-based, very niche area with very few groups working on them. I guess those are the kind of efforts that are clubbed together in calling biopower in the slides that I showed. Remember, I've given the source of most of those slides. Many of them are from Bloomberg or ExxonMobil, etc. Okay, so I suspect that they're clubbing those kind of efforts together into one group.
Okay, sir, I'm going to next question. So from Sharni Kacharia, does ITER could be a way out to meet this challenge?
If we can get a economical way of generating power from fusion, not from fission. And nuclear power, the normal thing that we know of is the fission, which is the using radioactive materials that are spontaneously breaking up and giving rise to energy. Fusion generated energy. I mean, that's actually the photovoltaic, the source is fission. It's a fission that's going on in the sun, right? So if we can do that, and that's why there are efforts. I've seen a recent flash news. Again, it's not an area that I keep track of, but if it is successful, it will be absolutely fantastic. And it will completely change the scenario. If tomorrow I have an technologically feasible and economically viable methodology of making fusion-based reactors, then I think the entire scenario of generation as well as research will completely change overnight. Change absolutely overnight. In fact, there have been a lot of efforts, but these are very expensive efforts, and that's why it needs multinational. So the ITER experiment that whoever is asking the question refers to is a very massive, very huge, intensive money and intensive effort that's going on. But I saw a news flash, I didn't read through very carefully, that talked about, for the first time, the first result came about a week ago or 2 weeks ago, where one event of such a fusion-based inner reactor gave more energy than the energy input. So far, all efforts, more energy is going in than it is generating. So we'll have to wait for some more time, I suspect.
Okay,
Deeptashika, I think we can go for the next question. The last question you can take a bit first.
Okay. So the last question is actually why is nuclear power not given more push?
These are very difficult.
I mean, there is a continuation to that. Sorry, sir.
Yeah, sure.
The question is, why is nuclear power not given more push? There is no air pollution and power cut unit of fuel is very high. That's the complete statement.
I can only tell the person who asked this question is a very young person who was not born when Chernobyl happened. And Chernobyl caused the kind of, oh no, but then Fukushima has happened since then, right? And so talking about pollution, it happens rarely, but there are 3 accidents that the general population knows of. If there's any other that happened we don't know of, Long Island, very close to accident that had happened a long time back, but nothing dangerous happened. It was contained before. Chernobyl accident happened, and it contaminated. Chernobyl is way into Russia. And within a couple of days, in Sweden, all the grass fields and the milk that was coming out of the cows were radioactive. So you can imagine, and that cannot be contained. It travels without visa and passport. It was all over the place, and people couldn't use. There are fields even today where people cannot use to produce anything. Fukushima, the tragedy that happened because of a natural disaster, and our this tremendous dependence on and belief that we are not vulnerable. So accidents do happen. And in nuclear power, if accident happens, the cost of it is huge. So on one hand, this is one of those situations where you can neither throw it away, nor can you completely embrace it. And human species as a society is grappling with this without a clear answer. That yes, it is cheap at some level. If you have to put in all the safety measures in place, it's no longer that cheap. And then also the waste fuel, what you do with it. There's some very, very difficult questions. You have to contain them for millions of years. How long do you want human species to exist? If you want them to exist for 1,000 years, 10,000 years, then you have to find a way of storing these nuclear waste fuels that long, because they're very long lived. And you think that you have a technology that will do it, and then another natural disaster would happen like Fukushima, and all your containers would break open and get scattered all over. So I'm not arguing necessarily to oppose it. I'm saying one cannot think that there is no pollutant. The pollutants there are few and far between, but much, much more dangerous and much more long lasting, and also virtually impossible to clean up. All the radioactive water that has gone into the ocean with Fukushima, we don't even know what would be the consequence of that in the long term on the marine life, and consequently on the life of humans that depend on the marine life. Okay.
Okay, sir. So should I take another question, or I will go?
It's up to you.
Okay, sir. Actually, one long question is here from Dr. S.S. Ali. Actually, he have two questions. First one is talking at the backdrop of COP26 and the goals targeted thereof. Do you think the various governments in the world are doing enough to achieve the goals? When we talk about the carbon space availability and the fossil fuel availability, this is the first question.
I can only tell my young friend that I really hope and wish that they are.
Yeah.
Because if they don't, we're in serious trouble.
Yeah.
That's absolutely for certain. I mean, you really don't know what we are facing. And the day it happens, it'll be too late to start doing anything about it. That is the problem of catastrophe. That is the problem of catastrophe. When it happens with such a space that you cannot respond to it. So I can only hope that, yes, they are doing.
And second question from him is, what is your opinion about not exploring the human energy uses behavior much towards making the efforts and plans sustainable, particularly for demand side management?
Now, it's a non-specific question because human energy, I do not know what the person has in mind, because using humans as fuel or, or even the mechanical energy or the thermal energy. We are constantly dissipating thermal energy. We're constantly dissipating mechanical energy. And let me tell you, there are serious efforts at harnessing those energies. These are very low level energies. But for example, I mean, this watch of mine this watch of mine, every morning when I go running, I wear this one. The reason being, this watch is a mechanical watch, but it harvests the energy of my running and keeps working. The day I don't go for running, it stops. So it reminds me that I have not gone for running. So basically, I'm harvesting the mechanical energy. There's more efficient ways of harvesting energy, and that is being used. Piezoelectric. In fact, you are constantly using that. Those of you who have seen or played with the stove lighter, You press a knob, it makes a click noise, and there's a spark. Where is that spark coming from? Because there's a piezoelectric material inside, and there's a hammer. When you're pressing it, there's a spring loaded and suddenly goes and hits. The piezoelectric, because of this mechanical deformation, develops suddenly voltage across, and that sparks across the terminal, giving rise to that spark. So you're harvesting your energy. And people are talking about harvesting thermal energy also, so that the devices that you wear will be harvesting with thermoelectric, will try to harvest your body temperature to generate low-level power, which would be enough to power the sensors that are on your body. And there are going to be more and more sensors on your body, right? I mean, I have all these, I love those gadgets. So I have something that measures even my cardiogram, ECG, right? Or monitors my heart all the time. Right now they have batteries inside, and once in a while I have to charge the batteries, but there are devices coming up which will try to charge part of it from harvesting these and harvesting many other loads. There's always an electromagnetic background that can be harvested. So all this harvesting is going on. Efforts are going on, let's say. They have to be economically. Yes, please.
Dr. Das, since you have allowed me to unmute, can I say something?
If you are not one of those who took over the proceedings before.
No, sir. Thank you. Thank you.
You are not the one dancing around on the screen, right?
No.
It was, they should know that it didn't bother anybody, because if it doesn't bother you, then they will not have any motivation.
No, sir. I'm an ex-defense veteran.
Okay.
And I have got over 4 decades of experience.
Okay.
And my PhD is in energy conservation, particularly with respect to the human behavior.
Okay.
And I was the one who asked those 2 questions, and you are answering the second one.
Okay.
I requested Dr. Das to unmute me, because perhaps my question was not understood correctly as you anticipated at the beginning itself. And that is why I thought, let me rephrase it if you allow me.
Please.
My question was at the backdrop of first world energy crisis, which was experienced in 1973, and demand side management was thought to be the solution. And it failed, though it substantially achieved many things technologically, but it failed because the race between demand and supply, it is like cat and mouse. It was because it was not sustainable. And the question what I asked, I will give you an example. Let us say 1 ton, 2 air conditioner of the same make with same specification operating in 2 different offices of the same size in the same city will not consume equal amount of power. It will consume 2 unequal amount of power, because the persons, and this is where the human behavior comes into being. And since 2007, 2008, a lot of studies are being done, though it has not been taken up seriously by the governments. And my question was from that background, that if we have learned from the mistake what we did in 1973-74 from demand side management, and today when we are restarting with a big enthusiasm and initiative, I see, because I'm not from academic world, I'm from the industry world, and it is from my research work and the experience, I see this is grossly neglected. Thank you, sir.
I understand. For the sake of time, let me give a quick answer. Again, quick answer, I'm not an expert. Maybe you are a better expert and in a better position to answer, but looking at the world and the way the world is going, I personally believe, if you remember, sometimes back, there used to be even on the TV advertisement coming, asking you to switch off the light when you're leaving the room. And there were stickers in all the offices, everywhere. Have you switched off the light, etc. In order to influence the human behavior. But I think, eventually everything has to make economical sense for it to be accepted and adapted into society. If it doesn't make money, nobody's going to do it. Unfortunately, Nobody does anything because of ulterior motive. Nobody does something because my grandchildren's grandchildren will have a better life. We are very short-sighted as human beings. And given that, so one understood that this was not saving enough money. And that kind of advertisement, that drive has totally gone out now. But what has happened now, I find that in most of the places, particularly abroad, they'll automatically have timers and sensors. The light will switch itself off. If there is no movement, it detects beyond the office hours. And as soon as it detects a movement, it will switch on the light. So basically, it has taken over the decision making and is doing it by machine rather than by the human being, because in order to change the human behavior and to appeal to the good sense of the human being, doesn't seem to have worked. And not only in the energy sector, in any sector, unfortunately. We'll not go into the more detailed discussion and more widespread discussion, but appealing to human sense for better behavior hasn't had much success.
Absolutely.
So, yeah.
Thank you, sir, for taking up those questions. So this is the last one, I guess. I can see Dr. Arunashish Laik has raised his hand. So over to you, Dr. Laik. If you have any question, you can please ask.
Yeah. Didi, if you don't mind, may I ask you the last question?
Well, I mean, that the organizers have to mind or not mind. I'll take any question.
Not at all. Not
Whether
at
it
all.
is last or not is up to them.
Okay, thank you. My question was regarding the efficiency of light, and nowadays, of course, all of us have moved very fast towards using LED bulbs in terms of lighting. What is your thought about the chromaticity of the light, what you are using nowadays from the LEDs? Are you comfortable?
Okay, I mean, I think those are, and those I think is very easily addressable. The chromaticity as well as the shift of the chromaticity with use. There are two factors that one has to worry about. Not just starting chromaticity, also with stability of the chromaticity with time. And I think those are technical and technological issues, and they have been largely taken care of. Whether I like it or not, this is a bit of a being used to idea. I mean, I was used to one kind of light, and my children prefer another kind of light because they got exposed to another. Their children would be used to another kind of light. So I think the shades, changing the shades to suit the time and culture is possible. And so color would actually change accordingly. So I don't think that is a very serious issue.
Okay, sir. Thank you so much, sir. So with this, we have come to the end of this Q&A session, and I'm really thankful to sir that after we got delayed by over an hour, you still took all these questions. So thank you very much for that. And now I think I'd like to request Dr. Niyogi for the vote of thanks.
I am audible now?
Yes.
Okay, so first of all, I would like to thank and my deep regards to our sir, Professor D.D. Sharma, for his wonderful talk. And I am all at the beginning of the discussion, when I give one email that it is basically an academic event, and the power of discussion at the end of the event, we have found that it is really a fruitful academic event. Although there is some unhappiness at the beginning, but we have come to the end with a good conclusion. So thank you very much, sir. In addition to this, I also thank the participants, because they are also the main attraction of this academic program, the students, the young faculty members like me. So without their support, this is not going to happen. I also like to thank our respected Dean sir, because he is also all the time encouraging us to conduct this kind of academic events. And we are really very much grateful to him. In addition to this, I would like to thank the IT support team of our university, because they provide us just kind of platform to conduct this kind of academic event. In addition, I would like to thank our all team members of the department and all team members, all faculty members of the School of Basic and Applied Sciences for their constant help and support. And finally, to all the members of our Adams University, so that we can able to conduct such an academic event online platform. So, sir, thank you very much. As we cannot meet in a physical interaction mode, but I hope that in near future, this pandemic situation will be stopped, will be over. And maybe whenever this is over, I will request you, if you come in Kolkata, and if we can connect with you, I think I will try to connect with you. Please come to our campus. It is really a very good campus. And I hope we can all have so much academic activities, so much learning things from your side. And but the thing is that something is not happening at the beginning. Sorry for this, but I hope that.
I mean, I would add a sentence, don't even think or mention them, because whoever does such mischief, what they're doing is for getting the attention. If you don't give them the attention, just ignore. That didn't happen. We wanted to have our meeting, we have met, we have finished, we're all happy, that's it. Don't mention them because they don't exist. They're looking for grabbing attention. Don't give them that happiness. It didn't happen, don't worry. It just didn't happen.
So if you ever come to Kolkata, as Sharif sir said, so we will be really lucky to have you, to welcome you in our campus. Please visit us.
Kolkata is where I grew up, and Kolkata is where I love to go very often. In the month of May, I should be coming.
Okay, so if possible, please visit our campus one. You will like it, definitely.
Thank you. Thank you very much. Actually, I was just talking to the IT person that how it happened. It's the first time, I think, we have been organizing so many events. And he said that, sir, the whole link was hacked. So the unmute and mute, all these controls were in their hands. So that was, I think, some kind of funny professional.
Yeah.
I hope they will also conserve their energy for positive ways.
Exactly. I'm sure they're young people. They get kicks out of it. Sooner or later, they'll all come back and do good things for the world.
Yes.
So forget them, forgive them, love them, be gentle to them also. They're our children.
Yes, sir. So thank you, sir. Thank you very much.
Thank you. I take you.
Thank you, sir.
Thank you.
So with this note, we have come to an end of this session. Thank you all for joining. Thank you very much. Okay, sir. Bye.
Okay, sir.
Thank you, sir.